Video is about the topic Nash equilibrium. It's a kind of game theory. So, what is Nash equilibrium? Nash equilibrium is a condition in which all the players playing the game accept. Okay, so accept that there is no better solution to the game than the current situation. So all the players actually playing the game accept that there is no better solution to the game than the current situation. No player would gain anything after changing their current strategy. So any new decision made by the players will not result in anything better. So in simple terms, if I have to say, the Nash equilibrium is a state in a game where no player can improve the situation by changing their strategy alone. So there won't be any benefit if player tries to change the situation or trying to alter the strategy alone. That's what I've said here. So it's a state in a game where no player can improve the situation by changing the strategy alone, assuming that other players keep the strategies unchanged. Okay, so it's a state of strategic stability. So this is important, strategic stability. The no one has the incentive to deviate. So this is what we have to understand. So means in a it's a state where no one has incentive to deviate, right? So what is that one? Actually we shall discuss with one classic example of a prisoner's dilemma. So whatever the theory that I've discussed here, so uh, that you guys will have better clarity when that we discuss about the prisoner dilemma. So yeah, so this is what the one example that I consider, that is a prisoner's dilemma. So imagine two suspects, player A and player B. They are arrested. So police actually separate them and offer a deal. So what is that one? They have two choices. So what is the deal that is offered? They have two choices. One is stay silent. So you cooperate with each other. That is, player and the player B should, or prisoner, instead of saying player or the prisoner, okay, prisoner and the prisoner B. So they should actually stay silent. They should cooperate with each other, or they should confess. So so that actually when they confess, actually they are betraying the other person, right? So here are the potential outcomes. That is years in prison. So if prayer A stays silent, there are four outcomes that we can have it as we can see here. If player, that is prisoner A, stays silent, okay. Please actually make the correction, instead of player, you can write it prisoner A. So this prisoner A, if actually he stays silent and prisoner B stays silent, that would result in the least sentence, that both could get only 1 year. If prisoner A stays silent and prisoner B confess, then when that's what, there's no incentive to deviate. That's what I discussed here. No one has incentive to deviate here, right? If there is a deviation here, means one person is cheating, so there is a deviation. Means a prisoner A stays silent, whereas prisoner B confesses. At that time, what happens? A gets 10 years, whereas B gets 0 here, right? Similarly, you can just observe here. Here also, prisoner A confesses, whereas prisoner B remains silent. When he confesses, he gets 0, but since he has remained silent, B gets 10 years. But whereas here you can just observe here, prisoner A confesses, prisoner B also confesses. Both get 5 years. If both actually remain silent, that would result in the least sentence of 1 year. If they deviate, then one of them will definitely get 10 years. That's a maximum. Whereas again, both actually somehow confesses, both actually deceive, then that actually, at least since there is a 5 years, 5 years is still better than 10 years. So this is what, so no strategic stability means no one has the incentive to deviate. Means this, see, in this case both prisoner and prisoner B, they are not deviating. Here also the confessor, both prisoner A and the prisoner B are not deviating. Both actually are confessing. That also would result in somewhat lesser punishment of 5 years when compared to the 10 years they would get if both people deviate. That is, if person A remains silent and prisoner A remains silent and prisoner B confesses, that will result in 10 years. Whereas prisoner A confesses and prisoner B is silent, there is a deviation, right? So here also both would get 10 years. So here in this case, there is no incentive for any of the prisoner to remain to deviate from one another. So that is what the Nash equilibrium is all about. Okay, what is this equilibrium? We'll discuss. Whatever that I have mentioned here, the same thing is written here, just in a table form, like in a matrix form, sorry, in a matrix form, whereas player A, player B, again, right, player A, prisoner B, which is fine. The same thing what is given textbook I mentioned here, player A and the player B. So both cooperating, both would get 1 year. One cooperates and one defects, that is the confessors, or both there is a deviation here. Since so one would get 10 year and then B would get 0 year. If player A actually defects whereas player B cooperates, so he would get 0 year and then he would get 10 years. Both actually defect, so both would get 5 years. The same thing whatever discussed here, the same thing has been put in the matrix form here. So what is this logical walkthrough? This is important that we have to understand here, right? See, to find the Nash equilibrium, so we have to look at the game through the eyes of player A and ask, what is my best move, right? Um, so what is my best move? So what happens here is that in scenario one, there is a scenario one. Player B stays silent. So when player B stays silent, then he understands that if A stays silent, A gets 1 here. So see, so player A is going to ask himself, what is my best move regardless of what B does? So player A is going to ask, what is my best move regardless of what B does, regardless of what B does. So if A stays silent, A gets 1 year. Okay, means if B has remained silent. If B has remained silent, so if A stays silent, A will get 1 year. If A confesses, A gets 0 years. That is true, right? Because A has deviated from player B and he will get 0 year, but B will get 10 years. But if A stays silent, A will get 1 year. So he understands that in these two cases, you can just observe here, either it is 1 year or 0 years. So decision actually he understands that he is going to confess because 0 is the least here. In the scenario 2, player B confesses. The player B confesses, A remains. If A stays silent, he will take 10 years, whereas if A confesses, he will get 5 years. So in this case scenario also, the resultant is A should confess. So guys, you can just observe here. If B stays silent, he is going to see that one. If A stays silent, I will get only 1 year. If A confesses, he will get 0 year. The least among these two things, he understands that so A should confess. Again, similarly, if B confesses, okay, so if B confesses, he understands that if that person, prisoner B, is going to confess, in that case, if that is, if A stays silent, then A will get 10 years. Right, sorry, yeah, he will get 10 years, but if A confesses, A gets 5 years. So which is the best among these two things? That is A confessing only. So here also the resultant is A confessing. As you can see here, this is important. In both the scenarios, the ideal situation is confess. So this is the result regardless of what player B does, whether he stays silent. If he stays silent, the decision is confess. If he confesses, the player B confesses, then also the A should confess. So regardless of what player B does, player A's best strategy is always to confess. This is called dominant strategy, right? Since a game is symmetric, that we have to understand, we already discussed that one in the earlier video, that is the game is symmetric. Player B goes through the exact same logic and he also decides to confess, right? So this is what is the logical walkthrough. That is, we have the prisoner's dilemma, that is where in both the scenarios, whether player B stays silent or player B confesses, the best case among these two things is always the A confessing. Since it is a symmetric game, that player A also, he also decides to do it in the similar way. That is, if he also analyzes, player B also analyzes that if player A stays silent, then the best thing would be confessing for B. And if player A again he confesses, that case also the best thing for a player B would be confessing. So player B also goes to the exact same logic and also decides to confess. So this is the logical walkthrough. So finally, what is the equilibrium? The equilibrium, the game settles at the bottom right corner. this one. So this bottom right corner, um, it settles that both actually confess. So this is they get a sentence for 5 years, right? So why is this Nash equilibrium? This you have to understand. Once they're both at the confess, neither can switch to silent without hurting themselves, because switching would turn their 5 year sentence into 10-year sentence. There is no incentive for them to deviate. This is what we have to understand, because both would agree that both would confessing is the better thing, because that would not hurt themselves. That is switching, one remains silent means that would reward into a 10-year sentence. They are stuck there. That is, both will confess. What is the paradox here? See, the one thing what you have to understand is that notice that the top left corner, that is this one, right? So in the top left corner, if both actually silent is equal to 1 year each, that's a better outcome for both of them. However, they cannot reach it because this is important. They cannot trust the other person. No trust, right? They cannot trust the other person. If they try to go for the good outcome, they risk getting the worst outcome. That is 10 years punishment. So what both would do is that they would confess it, so that actually at least they would get 5 years instead of getting the 10 years, even though the best outcome would have been if they remained silent, that is 1 year. So this is the Nash equilibrium where both can confess at 5 5, and that would actually help them getting the somewhat reasonable outcome. Okay, thank you.